project you just saw uses the unmodified Unity 6 engine on a 4090 GPU. Unity 6 brings a lot of improvements across the board, giving us better visual quality, enhanced realism, and improved performance for complex game imagery. For example, in just this one scene, we have multiple animated characters, a detailed environment, tons of VFX with dynamic six-way lighting, volumetrics, clouds, real-time shadows, and millions of blades of grass. So how did we fit all of this into the demo in real time? Let us look at some of the ways in which Unity 6 features helped us.
So first, let's look at the lighting. To get high-quality results, a scene will typically require different lighting setups in different parts of the scene. For example, this trench is a pretty tight space with lots of irregular surfaces for light to bounce off. But over here, we have a wide-open plane where the lighting is more or less uniform. Unity 6 includes the new Adaptive Probe Volumes feature, which automatically places light probes where they're most needed. So when I visualize the probes, you can see that the ones in the trench are much more dense than the ones out on the plane, capturing more detailed changes in the lighting. Scenario blending lets us bake different states of the lighting setups and blend between them. Here, we have separate lighting scenarios for different times of the day in the same environment. Changing the sun angle and ambient color is accomplished through real-time lighting, but the baked lighting scenarios now also allow us to change the indirect lighting to match. Next, let's look at the vegetation, the trees and grass that bring this world to life. There are more than 12 million instances of vegetation in this scene. That's a big challenge for both authoring and rendering. We used Houdini to scatter our trees and grasses, exported their basic properties into Unity as point clouds, and then used that data to create entities in Dot's ECS. Our ECS baking systems produce entities for each piece of vegetation, as well as creating imposters for clusters of vegetation that can be used at distance. So right now, we've streamed in about 8 million pieces of vegetation in the imposters, and another 480,000 as individual entities. So we have nearly 8.5 million pieces of vegetation active, but we're passing fewer than 500,000 entities to the graphics system.
So that is how we brought this world to life. But there is one more thing that we want to talk about in Time Ghost that we think points to some really cool possibilities. Achieving complex deformation for something like detailed cloth movement takes a lot of computing power. So traditionally, we've had to choose between creating at a high level of fidelity or creating in real time. There are already advanced DCC solutions for authoring cloth simulations for pre-rendered offline content, like Marvelous Designer or Houdini. But bringing that level of realism and sophistication into game development has always been a challenge. So, what if we could take a large, complex data set describing cloth movement and turn it into something fast enough to run in real time and small enough to fit in memory? At its heart, this is a compression issue, a space where AI has been used to solve problems for decades. So an artist on our team created a custom AI model to approximate these high-quality deformations, then apply them in real time using Unity Sentis, a package for Unity 6 that lets you bring AI models into the Unity runtime.
To train our own AI model, we used DCC tools to create 2,000 frames of animation to simulate the cloth movement on our high-resolution mesh. This looked great, but the data we'd produced was over 2.5 gigabytes in size. So we processed the data to extract the character's joint orientations and the resulting vertex deformations. Then we used the machine learning framework to train our custom AI model to predict these matching pairs of inputs and outputs. Training the model took about an hour on a desktop PC. And once that was done, we had an AI model that we could run in our project with Sentis to bring high-quality deformations at runtime. And there was only about 50 megabytes on disk. So now our protagonist's full costume deforms in 0.8 milliseconds per frame, and it looks just as good as the high-quality deformations that we computed offline.
If you want to get your hands on this demo, you won't have to wait long. We'll be releasing scenes with the environment and the character using the cloth deformation you just saw. They'll be available alongside Unity 6 next month.
We used a lot of our new tools and features to make Time Ghost, because we want to dog food the release and push the limits of this tag. Let's see what other early adopters are doing with it.
Thank you for the pre-recorded intro, Simon. I'm joined by Mike from Unity, who will help me out. Yeah, he deserves an applause. Starting out, we intended for Den of Wolves to be made with Unity 2022 LTS. But after seeing the improvements in Unity 6, both in terms of performance and rendering quality, upgrading became an obvious win. Upgrading is always scary, you all know this, but upgrading to Unity 6 was surprisingly easy, especially considering we did it mid-development. We wanted to move as much heavy lifting as possible from the CPU to the GPU and make everything else on the CPU as performant as we could. The first part means Unity 6 HDRP, and the second means dots. Sadly, I can't reveal too much about the game and how we're leveraging dots today. My PR team would kill me. But what I can show you today is how we're using some of the tools from the Unity 6 rendering tech stack to achieve our vision. So, here we have a pre-alpha test scene from the game, which is using Unity HDRP. As we look around, you can see how we're using various lighting elements, structural objects, and decals. We all know that managing draw calls in the game is important, and when we created GTFO, we had our own solution for this. However, the new GPU resident drawer in Unit 6 handles this out of the box.
Now, while turning it on here doesn't seem to affect much, I've just reduced the draw call batches by around 45%. Additionally, this wraps the batch renderer group's low-level API, which is foundational to other important features we'll look at.
Absolutely. Also, while likely getting our hands dirty with low-level API later on in production, in the meantime, it's awesome to just click a checkbox to get a reduction in draw calls during the prototyping stages. One of the major benefits of using the drawer is that it also enables us to use GPU occlusion culling.
Bam.
As you might guess, this feature pushes the occlusion calculations from the CPU to the GPU, which takes advantage of the GPU's ability to handle large amounts of data at the same time. Then there's spatial temporal post-processing, which is a mouthful, but it allows us to upscale from lower resolution to high resolutions performantly with limited loss of fidelity.
And while Den of Wolves targets PC for early access, they do plan to also target console at a later time. Luckily, SDP is hardware agnostic. It works at a range of devices from mobile to console, HDRP and URP, all with a low overhead. Furthermore, supporting DirectX 12 in Unity 6 is a big and important jump for our users.
Indeed. Using the new DirectX 12 updates makes multi-threaded operations more efficient, distributing the workload across multiple CPU cores with split graphics jobs for rendering. DX12 also supports advanced tessellation and shading techniques, so we can get even more detailed and realistic graphics. Now, Mike, let's talk about lighting.
Sure. So we believe that ray tracing is absolutely crucial for our users who want to achieve the highest levels of graphical fidelity. That's why we've recently added optimizations such as solid angle culling. DirectX 12 also supports ray tracing focused hardware, such as NVIDIA's RTX GPUs.
Add to that a more flexible pipeline, and we have the tools we need to create highly realistic lighting, shadows, and reflections that significantly improve the visual quality of the game. We also need a performant global illumination, but manually placing thousands of light probes requires hundreds of hours of work, and this is something we just wouldn't do. I did ask our art director about it, and he said a flat no. Instead, using the new adaptive probe volumes, or as the cool kids call them, APVs, saves us a ton of time.
So as you've already seen today, APVs allow you to place an automatic geometry-driven probe volume that gives you higher quality per pixel lighting in your scene. We've also added some new debugging features. So here, I'm examining the pixels in the scene to see which probes are contributing light values, so I can make adjustments as needed. There are more graphical debugging tools available, and together they make it easier to get things exactly how you want them, while avoiding problems like artifacts and light leaking.
There are many reasons why we choose Unit 6 for DenoVolves, and the cool thing is that they all work together efficiently.
1,000%. So, working with the folks from 10 Chambers on this test scene, we were able to achieve both increased visual fidelity and a 23% performance boost so far.
Yeah, it's been awesome to try out these features and seeing them in-game. And we've been partnering closely with engineers from Unity to provide feedback to the R&D teams who are continuously improving the tech stacks. You'll hopefully see them in action soon, and I'll see you in the Den of Wolves.